to cover the chapter 3 of our book. The title of this chapter is The Equation of a State. If you remember previously in chapter 2, we discussed the phase behavior of the single component and the two component mixture and multi component mixtures. And then we're studying how that phase changes as we change the pressure and temperature. But for the practical purposes, we really need to have an equation that can describe this behavior. So we cannot just simply do experiment for every single mixture to figure out, what's the state of the fluid, if we have gas, liquid, or two phase, or what are the quantities and the rest of the parameters. So for that reason, people they start developing different equation of states. And as we discussed earlier, usually what we do, we start with a very simple case. We start with a case that's simple enough to understand the behavior, and then we start adding the complexity as we go. Okay, so we are going to follow the same approach here. So we are going to start with the equation of a state for ideal gas, and then which basically we will go over the definition and the assumptions. And then when we understand the behavior of ideal gas, then what we are going to do, we are going to release the assumptions that we made to define this ideal gas to see what would be the real gas behavior. Okay, so for that, we are going to first cover the equation of a state, and then the ideal gas. We are going to visit some of the mixtures laws, and then we go over the behavior of the real gas. So as I said, properties of gases, they are different considerably from the properties of liquid, and simply because the gas molecules are much smaller and they are much further apart. Okay, therefore changes in pressure has much greater effect on the properties of gas, okay, such as density, okay, than the effect of pressure on, let's say, density of liquid. Okay, and generally we consider equation of a state as an equation that describes the relationship between pressure, volume, and temperature. Okay, most of the equations of states are developed based on the experiment, observations and empirical relationships. But we do also have the equation of a state, like virial equation of a state, that has an actual, physical base that you can just drive it from the first laws. Okay. So what is the ideal gas? Okay. So the ideal gas is a gas that has three main properties. These three main properties are as follows. Okay. So ideal gas is a gas at which the volume occupied by molecules is insignificant with respect to the volume of the total volume of the gas. So we know the volume of the gas is equal to the volume of the container that contains the gas. Okay, so same number of gas molecules, if I put it in a glass of water, type of thing, then the volume becomes the volume of the glass of water. If I just release it in the room, then it's going to be the volume of the room. So but the ideal gas says the volume of the gas molecules itself is negligible in compared to that total volume that the gas occupies. Okay, so it assumes the gas molecules, they basically have negligible volume. So, but it doesn't say that the gas volumes are zero. Okay, so the volume of the gas molecules are negligible in compared to the total volume of the gas. Okay. The second assumption is the intermolecular forces. Okay, in the case of ideal gas, we are assuming that the intermolecular forces are neglected. We know if we bring the gas molecules close together, there will be attraction forces, and then if we continue making them closer, then we will see the repulsion forces. However, in the ideal gas, we assume these intermolecular forces are neglected. Okay, so there is no intermolecular forces. And then the third assumption is all the collisions of the molecules are perfectly elastic. Okay, which means if these two molecules are coming and hitting each other with the velocity of a, they're going to go back with the same velocity. There is no loss of energy when these molecules are colliding. Okay, so it's a perfect collision. So these are the three assumptions of the ideal gas that you should remember and memorize it. This usually always been a closed book question. So what are the three main assumptions of the ideal gas? The volume of the gas molecules are neglected in compared to the total volume of gas. The intermolecular forces are neglected. There is no attraction or repulsion forces, and all the collisions are perfectly elastic. There is no loss of energy in molecules colliding each other. Okay. So how do we come up with the equation of a state? Okay. So the Boyle's and Charles equations are describing the volume, pressure, and volume temperature relationship. So we know when temperature is maintained constant, so at a constant temperature, volume of the gas is inversely proportional to the pressure. Okay. So if the temperature is constant, okay, we increase the volume, pressure goes down because the number of the molecules are the same. If you increase the volume, the number of the molecules per volume goes down, so the pressure goes down. If you remember, the pressure was the number of the molecules per unit volume. Okay, so if the volume goes up, the pressure goes down. So we know the volume has an inverse relationship with pressure. Okay, and we know any inequality can be converted to equality using the inequality constant. So P times V, which means becomes constant. Okay. When pressure is maintained constant at a fixed pressure, volume of the gas is directly proportional to its temperature. Okay. So you increase the temperature, the molecule starts moving faster, and then they are getting away from each other, so they increase the volume goes up. So volume directly relates to the temperature, volume inversely relates to the pressure. So this volume direct relationship with temperature again can be converted to equality using the equality constant. So V over T becomes equal to a constant. Okay. So PV is constant, V over T is constant. And we know under the same conditions of pressure and temperature, equal volumes of ideal gas contains the same number of molecules. Okay, this is basically Avogadro's law, which says there are 2.73 times 10 to the power of 23 molecules per pound mole of ideal gas. Okay, so at a given pressure and temperature, one molecular weight of any ideal gas occupies the same volume as one molecular weight of any other ideal gas. Okay, so that's another law. So now we want to combine all these to come up with the equation of a state for an ideal gas. Okay, so we are going to combine Boyle's, Charles, and Avogadro's law. Okay, how we are going to do that? We are going to do this in two steps. Okay, in step one, let's assume we have a system at a pressure of P1, temperature of T1, and volume of V1. So we know the state of the fluid. In step one, we keep the temperature constant, and then we increase the pressure from P1 to P2. So the temperature is constant, we increase the pressure P1 to P2, therefore the volume will change. So V1 becomes equal to V. So in change in volume of gas during step one, we know at a constant temperature, pressure times volume is constant. So P1 times V1 should be equal to P2 times V. Okay. At a constant temperature, P times V was constant. That's the first law that we studied. That's the Boyle's law. So it says P1 times V1 is equal to P2 times V. So P1 times V1 is equal to P2 times V, or V is P1 V1 over P2. Okay, so this is the first step. So now we are at this stage where our temperature is still T1, the pressure is P2, and we have a system at a volume of V. This time we keep the pressure constant, okay, and we change the temperature to T2. So the pressure will stay constant, P2, temperature will increase that to T2, therefore the volume will increase to V2. So here we know V1, V over T1 is equal to V2 over T2. That was my second law, that's the Charles law, which was saying that at the constant pressure, V over volume and temperature, they had a direct relationship. So V over T1 is equal to V2 over T2. Or V becomes V2 times T1 over T2. So we have a V volume being equal to P1 V1 over P2, and the same volume being equal to V2 T1 over T2. So these two ratios are now equal to each other. And I can rearrange that such that P1 V1 over T1 becomes equal to P2 V2 over T2. If I continue repeating these steps, I will see that the P1 V1 over T1 becomes equal to P2 V2 over T2 becomes equal to P3 V3 over T3. Okay, and this becomes equal to a constant. Okay, I can write this for 1 mole of gas. Okay, so I can say P times molar volume over temperature is equal to constant. Okay, so PVM over T is equal to constant R. And this R, we call that a universal gas constant. Okay, so that's a universal gas constant. So here there is this thing that we want to make sure this is really a constant. So is R the same for all gases? So let's assume we have two gases, gas A and B, at the same pressure and temperature. So I can write this equation, this for gas A and for gas B. So if I write it for gas A, it says P times molar volume of A over T is equal to RA. Let's assume R is different for different gases. And if I write it for gas B, it's again pressure times molar volume of gas B over temperature is equal to RB. Okay? We said these two are at the same pressure and temperature. So the VMA, the molar volume of gas A, becomes equal to RA times T divided by P. This should be equal to the molar volume of B because of the Avogadro's law saying that the same number of molecules at the same temperature and pressure will be equal for different ideal gas. So VMA is equal to VMB based on the Avogadro's law. So if these two are the same, temperature and pressure are the same, so therefore RA should be equal to RB. Okay? So the constant R is actually the same for all the gases. And this actually comes again from the Avogadro's law, which says at a given pressure and temperature, 1 molar weight of any ideal gas occupies the same volume. So at the same pressure and temperature, ideal gas will contain the same molar volume. So if the molar volumes are the same, these two ratios should be the same, temperature and pressure are the same, so RA should be equal to RB. So this equation, PVM over T is equal to R, I can write it as PVM is equal to RT, okay? And this is basically called the ideal gas law or ideal gas equation of state. P times Vm is equal to RT, and Vm is simply the molar volume. I can write this equation for n number of moles of gas. So PV becomes nRT. In this case, P is pressure, V is volume, N is the number of moles, R universal gas constant, and T is a temperature. And N, number of moles, we know it's equal to mass, small m, over capital M, which is a molecular weight. So it could be PV equal to m, small m, over molecular weight times RT, or PV is equal to nRT. So here we have the N is small m, that's a mass of gas over the molecular weight. In this equation, we need to make sure about the dimensions. So if the pressure is PSI A, the volume is in cubic foot, the R is in Rankine, the temperature is in Rankine, and N is in pound mole, then R becomes 10.732, okay? So if the pressure is in PSI, temperature, we have to convert that to Rankine, volume is in cubic feet, then the R becomes 10.732, okay? We use this equation of a state for all different calculation of all different properties of an ideal gas, okay? So here is an example. So it says, assume methane is an ideal gas, find the mass of methane in 1000 psi and 68 degree Fahrenheit in a cylinder with a 3.2 cubic feet volume. So we are going to write the equation of a state, PV equal to nRT, or mass over molecular weight, RT. The question asks for M, mass, so mass becomes PMV over RT. Pressure, 1000 psi given. Molecular weight of methane, we know methane is CH4, so it's 16. Volume is given, 3.2. R is 10.732. And temperature, we convert that to Rankine by adding 460. And we can come up with the mass of 9.1.